after we have been investigating time-varying betas in our fourth exercise, we turn now our attention to the covariance matrix of the point estimator. So our fifth task is first use the first stock in the excess return matrix and estimate the point estimator via OLS. Then calculate the covariance matrix and estimate the t-statistics of the parameter estimates. What do you conclude? Second, estimate the point estimator and the corresponding t-statistics for all n stocks in the dataset and store the results in matrices. How many stocks exhibit significant alphas after controlling for the Farmer and Branch 3-factor model? So as notes here, we have obviously again the linear regression model, where our y vector is a t/1 vector of excess returns. Our x matrix is the regressor matrix, which has a dimension t/4 in our case, if we use the Farmer and Branch 3-factor model, and beta is the corresponding parameter vector, which has the dimension 4/1 in our case. And u is obviously the vector of residuals, which is also a t/1 vector, which has to have the same dimension as our y. We know already we have made use of this formula earlier. It's the OLS formula for getting the point estimator, the vector beta hat, which is x transposed x inverted times x transposed y. And now the formula for the covariance matrix of our point estimator beta hat, so the variance of beta hat, obviously is sigma square times x transposed x inverted. And again, this is only true if we assume that the residuals are distributed as normal, with zero mean and standard deviation of sigma square. So again, we have to use the first stock in our data set and calculate the covariance matrix. And then after estimating the covariance matrix, we have to retrieve the t-statistics. So how do we proceed? So the fifth task is obviously getting the covariance matrix. So how do we proceed? So first of all, again, we retrieve the first stock in excess form of our data matrix Y1 that we have already constructed. Well, we have this data matrix already here in our workspace. It's noted as Y1, and Y1 has a dimension 497 times 184. Retrieving the first stock, then we have a vector which has the dimension t/n, which is 497 by 1. So this is what we do. We define our y1 vector, the vector of excess returns for the first stock, because we want to have the first stock that is defined as the first column and all rows of our y1 matrix. So next, we define our regressor matrix. So we define a matrix which has a vector of ones in the first column. The dimension is t/1. Or t is already defined in our workspace. We don't need to do it one more time. So if we now press the button, press t, then we know MATLAB knows already it's 497. So we have a vector of obviously of 497 ones in the first column of our X matrix. Then we want also to add the matrix of risk factors. So now our X, if we define this as X matrix, now we have to do it one more time, obviously, or no, it's still here. So if we copy this into the works into the command window and paste it in, so what we get is obviously then a t/4 matrix, like we desired. Next, our well-known OLS formula, beta, which is now our point estimator, beta hat, obviously, is then given by x transpose times x to the power of -1, which means we take the inverse, times the regressor matrix X transposed times Y, which is the exact returns, which denotes the exact returns of the first asset in our data set. So then we know, if we go back to our formula, if we move this on the left-hand side, so we have the estimated residuals are given by Y minus the regressor matrix X times the estimated vector beta hat. So this is very simple. So U is equal with Y minus the regressor matrix X times our estimated vector B. So then we say, okay, sigma 2 denotes the estimated variance of our residual vector. Because we know in the formula we need to estimate this sigma square, which is this residual variance, which is a part of the formula here. So, and this is simply given by, we discussed it in the lecture a couple of times. It's the residual vector U, transposed times U. U is obviously t by 1. If you transpose it, it's 1 by t. 1 by t times t by 1 is 1 by 1. So what we have here is a scalar, 1 by 1, divided by the number of observations minus 4, because we have 4 parameters to be estimated in our regression. So that's the formula for the residual variance, sigma square. And now we can estimate the covariance for our point estimator beta, which is denoted here, COV underscore B, the covariance for B, which is then sigma square, or sigma 2, which is our residual variance, times, what is it? X transposed times X inverted. That's it. So then we can copy it in order to see what comes out here. Let's copy it into the command window and paste it in. And now just write co B, and then what we would get is a 4x4 matrix, right? Since we have 4 point estimator, our parameter vector has the dimension 4 by 1. Our covariance matrix needs to have the dimension 4 by 4. And exactly this is what comes out. What we have to do now is, we have our parameter vector B, beta hat. So we have to divide each point estimator by the corresponding square root of the corresponding element on the main diagonal of the covariance matrix. So in order to get the t-statistic of the alpha, we have to divide this guy here by the square root of the first element on the main diagonal. If we want to get the corresponding t-statistic for the exposure against the market factor, we have to take this second point estimator and divide it by the square root of the second element on the main diagonal of the covariance matrix. So, and that is what we'll do now. We will implement this using a for loop. First, we have to create a vector that stores our estimated t-statistics. Let's denote it as t underscore stat is equal with 0s, and we have 4 t-statistics to store. So it's a 4 by 1 vector then. Now it comes to a for loop. For I is equal, for I from 1 until 4, do what? So our store in t underscore stat at the position I, what do? We take the corresponding bi in our parameter vector and divide it by the square root of the element ii in our covariance matrix. And then we end the for loop. So if I is 1, we take the first element in our beta vector and divide it by the first element on the main diagonal. Very simple. If I goes to 2, we store in the second position of our t-statistic vector. We take the second guy from our parameter vector beta and divide it by the square root of the element 2, 2 on the covariance matrix. So that's exactly what we want to have. So next, we can just run it. So let's copy also the second part of the of this code, copy it into the command window, and let's write in. If you now write in t stat and push the enter button, MATLAB spits us out the corresponding t statistic, the corresponding t statistics that are in this vector. So, and obviously the alpha of the first stock has a t statistic of 2.54 over the sample period, which means that the Farmer and French three-factor model is not able to price the stock correctly given the sample period, because it obviously generates an alpha that is statistically significant on a 5% level, right? If we would test if the Farmer and French three-factor model can price the stock, we have to compare the t-statistic of the alpha with 1.96, which is a corresponding critical value of the normal distribution, if we have a significance level of 5%. What we see also is that the exposure against the market factor is positive because the t-statistic of the second guy here is positive, and we see is highly correlated with the market factor, which is maybe not so surprising. Next, we have here the exposure against the size factor is obviously negative. It's minus 0.45, and the t-statistic is minus 5.34, rounded, right? So this means that this stock significantly co-moves with the short leg. It's negatively correlated with the size factor, which means it co-moves with the short side of the size factor, which are big stocks, and this means that the first stock is obviously a big stock, right? So next we see that the exposure against the value factor is also negative. It's minus 0.17 in rounded figures, and the exposure and the t-statistic is negative 1.88. So on a 5% level, we cannot reject the null hypothesis that this point estimator is statistically 0. On a 5% level. So which means this stock is neither value stock nor a growth stock, at least not on a 5% significance level. So this is what we can conclude after having estimated the corresponding t-statistics based on the covariance matrix. So next, estimate the point estimator and the corresponding t-statistics for all n stocks in the dataset and store the results in matrices. How many stocks exhibit significance alphas after controlling for the Farmer and French three-factor model? So what do we have to do now? So we have to do this across all stocks. So do it for all stocks now. First of all, we want to store our results. We create a matrix. Capital P underscore B is equal to zeros, 4 and n. So obviously what we want to do is here, we want to store in each row the corresponding point estimator across our n stocks. So it's a 4 by n matrix. And here we store obviously in PB, it's for the point estimator beta hat, and we also need a matrix P T stat, which is equal to zeros, and also it has the same dimension, 4 by n. So and here we store the corresponding t-statistics in the same order as we store the point estimates, right? It has the same order. So what we do is very simple. We use a for loop for j, which is now which denotes the dimension of stocks, because we have n stocks on our sample. So j is from 1 until capital N, and n, we know it should be the dimension of stocks, and it is like that, right? It's 184, as we see. It's still stored in the command in the system here in MATLAB. So what we do is, okay, do something from j is 1, start with 1, then use 2, 3, 4 until capital N. So we do something capital N times. What do we do? Beta is equal with what? First, we have to do point estimator, so we can copy it from the code before. This obviously does not change much here. So that's our OLS regression, and obviously this part here of the OLS regression, the regressor matrix is the same for all stocks, right? We use the same three-factor model for pricing all of our N stocks. The only thing that changes, obviously, is here in the end, the regressant, the dependent variable. In each loop or in each iteration, this changes. So in the first iteration, if j is 1, we want to take the excess returns of the first stock. Yeah. So j is 1, yeah, take the first column and all rows of the excess return matrix. This is what it tells us here. So, and regress it on the Farmer and Friend three-factor model, yeah, which we have already defined earlier here. Very simple. The next step is, okay, once we have the corresponding point estimator, if j is 1, we get the OLS estimate for the first stock, and we need to store it somewhere. Okay, we want to store it in the matrix PB that we have just created before the for loop, right? So P underscore B, and now we have to get the dimension correct here. So we want to store it in the first column, yeah, in all 4 rows, yeah. In the first iteration, this is 1, and we have obviously 4 rows, so this means all rows, so 4 rows. So on you want to store, what do we store here? This has the dimension obviously 4 by 1, right? So we have to store, we can store the B like it is, we don't have to transpose it, right? So next, we have our, we can use the formula here above for the covariance. First, we have to get the regression residuals. Yeah, we copy that, or actually we can copy the whole code here more or less until here, right? We just have to make some changes, which we will see on the way. So first of all, we have to end this loop here, yeah, because we have always to end the for loop. So what changes here in the code? So obviously, the only thing that changes here is, okay, we have to use the residuals of the corresponding stock that we just used in the iteration. So it's obviously in this changes in each iteration, we get a new residual variance, yeah, that we have to calculate here. So, and this is then defined as U is equal with take the excess returns of stock J minus the regressor matrix times the corresponding point estimator beta that we estimated here in the beginning of the for loop. Yeah, and this changes in each iteration, right? Like this. The U changes also in each iteration. Because this changes, yeah? We use always a different independent variable. So, and sigma changes as well, obviously. Yeah, we see this is always overwritten. This changes in each iteration. And also the covariance, of course, changes in each iteration, always overwritten. So the t-statistic, it's the same, like we just could copy it here. It's the same thing, yeah. So what we have to add now here is we want to store, because it's overwritten in each iteration, but we want to store it for each stock in this matrix here that we defined before the for loop. So let's copy it here. So t stats, and it has the same dimension as our result matrix P underscore B, yeah. So if J is 1, what we have here is a 4 by 1 vector, yeah. So it's in the first column vector of this result matrix here. We want to store the results. So what comes here in must be the dimension. It must have the dimension of 4 by 1. And obviously, this t-stat vector that we have here estimated in this inner for loop has also the dimension 4 by 1, right? We know that already from our previous analysis. So we can just store our corresponding t-statistic for the current iteration here in this matrix. Yeah? So it's very obvious that in the second iteration, once this loop is completed, it goes back to j is 2. Yeah? And what happens then is we regress something on this second excess return vector of our y1 matrix. So then again, we get obviously a new b that we store here in the second column of our p underscore b matrix. Then j goes to 2. And again, we get a new residual vector, depending on our new estimated beta hat and on the excess returns of the second stock. We get a new residual variance denoted here as sigma 2. We get a new covariance matrix of the parameter vector beta. We get new t-statistics, of course. Everything is overwritten, and that's why we want to store it in our result matrices that we have to put, of course, before the for loop. And what you also see here, we have an outer for loop which ends here, and we have an inner for loop that ends here. So we have to end both for loops, otherwise we have an error message. So let's now do that. Let's now copy this part of the code. We do it step by step and paste it into the command window in our MATLAB program. Paste it in, push the enter button, and now let's have a look on our matrices. So in our p underscore b matrix that we can see in our workspace here, we see the corresponding point estimates. So we can plot it. Let's plot the alphas. The alphas are obviously in p underscore b and in the first row across stocks. That's wrong. So we have to obviously to do like this, because we have the first row and all columns, all entries in the first row. So we have this happens sometimes that you get it not straight. So obviously, if you do the code like if you write it like before, obviously it gives you all entries in the first column, and this is obviously 4 entries. So this is not what you want to have. We want to have the all entries in the first row, And now remember again, the first always gives you the row index, the second the column index. So we want to have all columns in the first row. So that's what we get now. So we have 184 stocks, obviously 148 alphas. We see here the distribution of our point estimators. So we have sometimes some alphas obviously are here around 1% per month. Some alphas are close to negative 1% per month. So there's a variation, a quite huge variation, because these are obviously given in terms of monthly returns. So we can also plot, let's plot the corresponding t-statistics, and they are given in the matrix. So one more time. So if you want to have the same command that we have in the previous here in the previous line, you just push the pile upwards, page up, and then it gives you the last command that you just entered in MATLAB. Okay, so let's take the corresponding t-statistics, and they are stored in p underscore t underscore stats, and in the first whole first row that we have stored the corresponding t-statistics. Let's plot those, and that's what we get. So we see obviously, we know 1.9, let's roughly 1.96 to be more precise. There we have our critical value, and we see already that here are some stocks that obviously have significant alphas, positive alphas, and also the other way around. Below minus 1.96, or let's say roughly -2, we have here obviously some stocks that generated significantly negative returns, in across our sample period. So next, we are asked how many stocks exhibit significant alphas after controlling for the Farman branch 3-factor model. We want to check now, okay, how many stocks do we have in the sample that have exactly alphas that are either above 1.96 or below minus 1.96, because those are the significant guys. Yeah. So how do we proceed? So first of all, let's create a vector A2. A2 should be the sorted vector of our t-statistics that are corresponding to our alpha. And we know already they are stored in P, in our matrix P underscore store underscore stats, and in the whole first row, yeah, which is here given by row 1, all entries. Okay, so we have to close that. Now we created a vector that sorts the corresponding t-statistics in an increasing order. If we copy this and we paste it in the command window, yeah, we will get these entries here. Yeah, so we see that there are some stocks that have a high alpha that is above 1.96. Yeah, and we have also some stocks here in the beginning that have t-statistics that are below minus 1.96. Yeah, either we can now count them, but if we have many stocks in a sample, it's better to write it in the code. So what we do is now we create a vector of zeros, create a vector of zeros that has the same dimension as our stocks have, which is n by 1, 184. We want to store here in this vector, we want to store all t-statistics that are either below minus 1.96 or above 1.96, which means we know then if we give in this vector, if we put a 1 in every entry whenever the t-statistic is above 1.96 or below minus 1.96, and then we just need to sum up this vector, and we have the number of stocks that have significant t-statistics, right? So very simple. But first of all, we have to create a vector of zeros, which we have done here. Then we start again with a for loop. Our for loop is from j equal to 1 to n. So if the element j in the vector A2, yeah, where we have now remember we have the sorted t-statistics here for the alpha. So if the element j in A2 is smaller or equal to minus 1.96, then what then? Then a in the vector A22 element j should be equal to 1. Or moreover, it's then else if, obviously, if the element j in vector A2 is larger or equal 1.96, which is obviously the critical value of the upper part of the normal distribution. What is then? Then we want to have also a 1 in entry j of the A22 vector, yeah? Because we are collecting now, want to know where are the significant t-statistics. So else, what if none of these is true? Well, then the element should remain a 0. Yeah? The element j should otherwise remain a 0. Now we have to end the if command and we have to end the for loop. Now this is always what we have to do. Yeah? So then we can copy this code here, this part of the code, yeah, into the command window, and let's see what comes out. So now let's take the sum of our vector A22, and this is obviously not true. So now we have to check where it has gone wrong. So yes, obviously here, yeah, of course, here you see we have to write minus. Yeah, if element j in the vector A2 is smaller or equal to minus 1.96. And here the second if command, or the second condition, this is correct. It should be larger than 1.96. So again, let's use Let's copy this code here. So sometimes you see it can go wrong. So and now let's take the sum of A22 and it's 16. And it should be 16. Let's double check. Let's take our vector A2, which has the sorted t statistics for the alpha. So what we see is here, there is 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5 entries that have a value above 1.96. Now we have to add, we have also to calculate how many values have a t statistic below minus 1.96. And this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 plus 5 is 16, at least in my word. So this is what comes out. So obviously, out of 184 stocks, we have in this standard framework, we have obviously 16 stocks that have a significant alpha. So which means that roughly 8.7% of the survivor stocks in the S&P 500 index have alphas, which means that the Farmer and French three-factor model cannot price these stocks correctly. So obviously, we have also been discussing the problem with these tests. So obviously, what we have to do is actually, if we want to make a if we want to come to a conclusion, we have to test these parameters jointly, because obviously the alphas are correlated, which might have an impact on the test statistic. If the alphas would be completely uncorrelated, then we can exactly do what we just did. We can just calculate how many stocks generate alphas, significant alphas, and if this is more than 5%, on a 5% level, we would then reject the null hypothesis that the Farmer and French three-factor model is able to price this universe of stock correctly. But again, because the alphas may be correlated, we have to use a joint test. But this is obviously already a good indication, a good first indication. So what do we do next? Okay, we know that in financial markets, we have volatility clustering going on, which is a stylized fact. So obviously, our formula that we used here may be not correct. It could be incorrect if our residual variance is clustering, because now we might remember from our lectures, this formula assumes that the residual variance is the same across time. But we have seen this may be not always true. And now we want to implement a formal test for that, which is called the Rglm test. So the task is first, use again the first stock in the sample and perform an Rglm test using only an intercept in the mean equation and 5 legs of squared estimated residuals in the auxiliary regression equation. What do you conclude? So that's what we want to do now. So we are now in exercise number 6. And this is the Rglm test. So again, we should take the first stock. So let's grab again the first stock and let's denote it as small y. Small y is equal with y1. We take the first column vector of our excess return matrix. Again, we construct the regressor matrix. And in this case, in the first task, we should just have a vector of ones. We just have obviously an intercept term in the regression equation. And so this is what we do. Then our X matrix becomes simply a vector, a t by 1 vector of ones. Very simple. So then our beta is given by, now we have the standard formula again, X transposed X times X inverted inverted times x transposed times y. Yeah. So what we do is we just regress the guess returns on a vector of ones. This is basically what we do here. Then again, our residuals of the mean equation, yeah, this is our mean equation here. Obviously, we model here our mean equation. So our residuals of the mean equation are then simply given by y minus x prime times beta. Yeah, and our beta is just the parameter for the constant term of it's just the sample average basically of the excess returns. Yeah, very simple. So next we have formulated the mean equation. We have the residuals of the mean equation. Now we have to construct the auxiliary regression that we need for the test statistic, right? We hopefully remember from the lectures. So we create a vector, let's call it U2, and what we store in here, we want to store in the squared residuals here from the mean equation, yeah, because we need them for setting up the test statistic. So U2 is equal to zeros t by 1, yeah, has the same dimension as our residual vector, of course. So now we operate with the for loop for I is equal with 1 to t, 1 to capital T. So what do we do? The elements I in the vector U2 should be equal with UI squared. That's it, very simple. Now we constructed the squared residual. Yeah, let's have a look on how it looks like. Copy this code here into Matlab in the command window, paste it in. And now it says here that the regression, that the dimensions, something is wrong with the dimension. Let us see what has happened here. Yeah, exactly. Here we have to take away the prime. Yeah, it's the residual is defined as y minus x times beta, and not beta x prime. So again, let's copy this part of the code, paste it in, and now let's plot our squared residuals. Yeah, this is how it looks like, and we see already, because obviously the squared residuals are a proxy for the variance at time t, obviously we see that periods of high volatility are alternating with periods of low volatility, yeah, high volatility, low volatility. So we see already here there's a sort of clustering going on in the data. Yeah. So what do we do next is, okay, in order to implement the test statistic, we have to define we have to use an auxiliary regression. So we have to define now our dependent variable, yeah, let's denote it as y1, and y1, yeah, because it says in the exercise we have to use 5 legs, like we have also done in the lectures, if you remember correctly. So, and we know also that we lose the first 5 observations, yeah, from this vector u, from the squared residual vector denoted as u2. So we have to start at observation 6, 6 to capital T. So we take the observations, we start at observation 6 and take the all values until T. So what we have here now is a 184 minus 5 is a 178 by 1 vector, right? So this should be a 100, y1 should be a 179 by 1 vector. Let's check it. Paste it, and let's check what is y1. Sorry, yes, exactly. It's at 492 by 1 vector, yeah, because we had 497 is the original length of in the time dimension, and minus 5 is 492. So yeah, this is correct, obviously. So that's now our dependent variable. Yeah. So as a dependent variable, we have obviously the squared residuals, and as our X matrix, let's denote it as X1. What do we have in our regressor matrix? So first of all, we have a vector of ones, yeah? And because we lose 5 observations, the length of this vector of ones is now t minus 5. T minus 5 by 1. Yeah. So the next regressor is obviously in this the setup of this test statistic works out like this, that we have to lag our dependent variable. Yeah. So the first lag is obviously we can copy this here. It's obviously from 5 until t minus 1, right? So we have the first lag for this vector here is obviously the observation 5 until t minus 1. Yeah, obviously. And the next one would be then, we can just lag it by 1. So the next regressor would be then the observation 4 until t minus 2. The next regressor would be from 3 until t minus 3. Now we have 1, 2, 3 legs. Now we have to have then the next guy would be from observation 2 in this vector until t minus 4. And finally, we would have the last regressor, which is the fifth guy here, yeah, which goes from 1 until t minus 5. Yeah, you remember this erratum, yeah, that we had in detail on the whiteboard, yeah, where I derived this. So that's our regressor matrix for the auxiliary regression. We regress the vector of squared residuals on lags of the squared residuals. Yeah, this is what happens here, including, of course, a vector of ones. So, and you can think of it like this: under the null hypothesis, yeah, these guys here are 0, obviously, yeah, because if these guys here are 0, then and only the intercept term here would be significant. This would mean that we do not have volatility clustering going on, yeah, because then the lagged squared residuals do not have an impact on the future residuals, yeah, on the future squared residuals, yeah. So under the null hypothesis, obviously, we assume that there is no volatility clustering going on, and the residual variance is constant, which would mean that we can use this formula for the covariance matrix for our parameter vectors, right? So next, we have to define what is the parameter vector. Let's call it as beta 1 for the auxiliary regression. Yeah, it's a step in between. So it's defined as obviously x1, which is now this auxiliary regressor matrix, transposed times itself inverted times x1 transposed times u1, yeah, which is here defined as this guy. So now we get also the error term for the auxiliary regression. Let's note it as E, because we have U already for the mean equation. Yeah. So let's use E here as a residual vector. E is equal with Y1 minus X1, yeah, times beta 1. Yeah. This is now the residual for the auxiliary regression here that we have defined here. So then the R square, which is the coefficient of determination, which shows us how much this model here explains in the auxiliary regression. Yeah. So the R square is the R square of the auxiliary regression, and it's defined as 1 minus the residual vector of the auxiliary regression, yeah, which is E transposed times itself divided by the variation in the dependent variable, which is y1 square transpose times itself, of course. This is the standard formula for the R square. So then we know the test statistic is given by, it's called lambda, have it denoted as lambda, is t times r square. And now we have to think about what is the corresponding critical value of the chi-square distribution with 5 degrees of freedom. So we can check it from the statistics table. The critical value for if you have a 5% significance level, the corresponding critical value is 11.07. Yeah, you will find the table for the chi-square distribution and the normal distribution in Moodle. So it's 11.07. So whenever this test statistic lambda exceeds 11.07, we would reject the null hypothesis of constant residual variance, and we would conclude that we have volatility clustering going on in the data. So let's do this. Yeah, let's copy the whole code and let's see what comes out. Paste it into the command window. So the test statistic is estimated at 120.16. So which means on any level, we reject the null hypothesis of constant residual variance, yeah, which means we have volatility clustering going on, and this formula here does not specify the covariance matrix of our point estimator correctly, yeah, because this guy here is not constant. Yeah, the sigma square, the residual variance is not constant. It is dependent on past squared residuals. Yeah. Next, second, use the first stock in the sample and perform an Rglm test using now the Farman-French three-factor model in the mean equation. And again, 5 legs of squared estimated residuals in the auxiliary regression equation. What do you conclude? So the only thing that changes now is that we model the mean equation differently. Yeah, you see here, we had obviously our x matrix, it's just a vector of ones. But now we want to have the Farman-French three-factor model here. So what we can do is, let's just copy everything. Yeah, or we can maybe just change the code, but oh no, let's just copy everything, it doesn't matter. Copy everything here. Rglm test using Farman and French model. Okay, so let's copy it here. So what we have to change is now our matrix here. So we have to define our X matrix. We have to add here our factor matrix, yeah, which we have defined as F. That's it. Our beta is now obviously 4 by 1 vector, yeah. So so hence our residuals here change. This changes here as well. Everything is overwritten, right? Everything will be overwritten. Now let's remember, here the test statistic was 120. Let's see what comes out if we use the Farman-French three-factor model. Yeah, let's copy the code again. Let's copy this part of the code. Yeah, paste it into the command window. What we see, the lambda is even higher now. Yeah, it's 141. 141. So let's just, for fun, plot this vector of squared residuals. Yeah? Obviously, much more extreme now. Yeah? It's much more extreme than it was when we just used the a constant in the model. Yeah. So this is pretty obvious that we have here volatility clustering going on in this data. So once we know that, once we know that we have volatility clustering going on and the variance, the residual variance is not the same across time, there is the so-called white correction that we can use in order to estimate the corresponding covariance matrix of our point estimator correctly. So at least this is all this is based upon asymptotic theory. So, but that's good enough for us for this purpose. So now the seventh task is implementing the white correction. So again, use the first stock in the sample, implement the white corrected covariance matrix, and calculate the corresponding t-statistics. So we remember here, as a note from the lectures, that we cannot simplify this equation here like we did earlier, like this in this form. Now we have something here in the middle, sort of a sandwich, this omega matrix, and we remember from the lectures, this omega matrix has on the main diagonal the corresponding squared residuals for each point in time. So this guy here, the omega, is a t by t matrix. If we have t time series observations, omega is always a t by t matrix. So on the main diagonal, we have t elements. The first element on this main diagonal is the squared residual of our mean equation. It's the squared residual for the first time series observation. The second element on this main diagonal is the corresponding second squared residual in our time series. Above and below the main diagonal, there are zeros, because we assume that there's no autocorrelation going on. So how do we implement this? This is what we will do now. So the seventh task is now the white correction. So again, we should take the first stock, which is defined as earlier, as the first vector of our excess return matrix. Then again, our X matrix is defined as having a vector of ones of dimension t by 1 in the first column, and of course the factor matrix consisting of the 3 risk factors as well. So X is again a t by 4 matrix. Then our beta, the formula for the beta, does not change, so we can actually copy this guy here, right, from above. It's always the same formula, you see, it's very simple. So obviously, all this implementing the white correction is a sort of a two-step procedure. So we have the standard OLS regression is sort of the first step. We get the residuals, u hat, and we know already the formula is u hat is equal with y minus x times beta. And these residuals here from the standard OLS regression are now used to set up the omega. Okay, so let's first, we discussed it in detail in the lectures. So let's first take an identity matrix. Let's define omega 1 as identity matrix, and the command for implementing the identity matrix in MATLAB is IT. It gives you a t by t matrix that has only ones on the main diagonal and zeros elsewhere. So let's copy this, so that just as you see, so that's it. That's how it looks like. So you see here already, it's on the main diagonal we have ones, and otherwise we have just zeros. So in our omega, there is where we want to store basically the corresponding squared residual entries on the main diagonal for each point in time. So our omega is then, we need to construct a zero matrix, zeros t by t. It's a t by t matrix, as we already said. Now we have two for loops. For I is 1 to capital T, and then for j is 1 to capital T. So what should we put in here? So our omega ij, so the element ij in our omega matrix, what should it be? So it should be omega 1 ij. This is which is the corresponding element on the identity matrix, yeah, because we have defined omega 1 here as the identity matrix. So for instance, if I is 1 and j is 1, yeah, so the element 1 1 in our omega matrix should be a 1 times what? Times ui squared, right? Let's end both for loops. So now we have to think a little bit what's going on here. So if I is 1 and j is 1, yeah, the first element in our omega matrix is this guy here is 1 because it's an identity matrix, and the first element, the element 1 1 in omega 1 is a 1. So we multiply 1, we multiply what is here, which is a 1, times the first element in our vector, in our residual vector, yeah, from the standard OLS regression, and square it. This is exactly what we want to have. So, and we put it, this is stored here on in our position 1 1 in our omega matrix. So what happens if I is 1 and j is 2? So if I is 1 and j is 2, we store in position 1 2 what is here in this matrix. The element 1 2 is a 0. Yeah, because only on the main diagonal, only if I and j is the same. Yeah, if I and j is the same, only then we have a 1. Otherwise, we have a 0. So it's 0 times something is 0. Yeah? And this is true for any other element as well. Only if I goes to 2 and j is 2, what is then? Yeah, then omega in the omega 1 matrix, we find again a 1, and we multiply it with the element, with the second element, yeah, because I is 2, and square it and put it then basically here in the position 2 2 of our omega matrix. Yeah. And what is also important to note is, so first we start with 1, and then we go to the second iteration here in the outer loop after we completed all iterations for the inner loop. Yeah. So first I is 1, and then j is 1, and then it goes, it keeps I is 1 constant, and then in the next iteration it goes to j is 2, then to j is 3, and so on until j is t. And after this is completed, it goes back to the outer loop, it goes to I is 2, and then again it starts with j is 1, 2, 3 until t. After this is completed, then it goes on to the next guy, and then I is 3. And then again it goes from j is 1 until capital T. So this is basically how these loops work out, and you can think at home how this basically then works out. It's very simple, basically. Just you have to go through it step by step, and then you will figure out exactly how it works. So now we have to implement this nasty guy here. Yeah, this long, because obviously we said from the lectures, in the lectures, we cannot simplify this, but we just have to plug it into MATLAB, and it does everything for you. So now we define the covariance from our point estimator beta as what? So it's X transpose, our regressor matrix, times X inverted times X transposed times our omega, this guy that we just constructed here, that is in the middle, times X times x transposed x inverted, and that's it. Yeah. So let's do that. And remember now, our covariance matrix should have the dimension 4 by 4. Yeah. So this covariance matrix here must have the same dimension as this covariance matrix here, right? It must be 4 by 4. And we derived this in the lecture. Let's paste it here in. Let's check first of all our omega. Yeah. We see here on the main diagonal, we have the squared residuals. Yeah. Let's, for instance, omega 1, 1, which is the first element in our omega matrix, it's 10.5. So the element 1 in our residual vector is 3.24. If we square this guy, it should be exactly 10.50, right? And voila, it's exactly what we want to have. That's the first element on the omega, and it corresponds to the squared first residual of our residual vector. Yeah. So now the covariance matrix, we said it should be 4 by 4, right? And voila, it's a 4 by 4 matrix. It must be like that. Now again, in order to get our t statistics, we have to divide each corresponding element in the parameter vector, in the estimated parameter vector, by the square root of each corresponding element on the main diagonal, or in this covariance matrix. So again, we compound. Let's store them in the vector t stat. T stat is a vector of zeros, 4 by 1, where we store the corresponding t statistics in. So for I is 1 to 4 to what? So store in t underscore stat element I. What do we store there? Well, take the point estimator bi that we have estimated here, yeah, and we know that the even if we have volatility clustering going on, this point estimator here is unbiased, right? We have derived this during the lecture. If you are unsure about it, then check it one more time. So we have to divide it by the square root of what? Of the covariance matrix element I, right? So the first guy, if I is 1, yeah, what do we store in the first element of our t underscore stat vector? So, well, we take the first guy, the first point estimator in our beta vector, and divide it by the square root of the first element on the main diagonal of our covariance matrix. Yeah. Then, if I is 2, what do? Okay, we store in the second element of our vector t underscore stat. We take the second element in our parameter vector and divide it by the square root of the corresponding second element on the main diagonal. Very simple. So then we end the for loop, and now we can just copy it into the command window. And now we can just plot it. Let's just spit it out. So we write t underscore stat and push the enter button. So then we get the corresponding t statistics. Yeah, this is what we see here. So the alpha is 2.5. The t statistic of the alpha is 2.5, which indicates that the Farmer and French 3-factor model cannot price this stock correctly. Yeah? The exposure against the market factor is also significant, but the t statistic, as we see, is now 9.24. Yeah, you remembered from earlier it was 11 point something, so obviously using the white correction has decreased the significance of the t-statistic corresponding to the market exposure. Yeah. So, and this is basically what comes out. You also remember here, this guy was, as I remember correctly, minus 1.88. Now it's minus 1.43. So if we use the standard t-statistics, we would on the 10% level, yeah, we would argue that this stock is a growth stock, yeah, because on the 10% level, yeah, minus 1.88 is still in the 10% significance level, but minus 1.43 is not. Yeah. So using the white correction, obviously, which is the correct way of implementing the t-statistics, gives us a different view on the significance, right? So it changes the statistical significance, and by this, it changes your statistical inference. So if you use the wrong t-statistics, yeah, you obviously end up with wrong statistical inference.